So we see that research design is fundamental to our analysis, and the degree to which our claims are anywhere near correct again, or sensible or informative, it depends on the research design in the first place. So let's talk a little bit about it. Years and years ago, it used to be common to just vary one factor at a time. So I measure my response for this level of the factor, and then I just change that factor to another thing and measure the response. And maybe I change now a second factor, measure the response, etc., etc. The point is that this was highly inefficient because it would require many experimental runs because we were just changing one of the factors to see if there is a difference between those two observations, and in that sense, try and see if there is a certain effect for that factor. But then in the 1920s, we started to have factorial designs along with analysis of variance, which we will cover in a few videos. And the advantage of factorial designs is that they allow us to change several factors at the same time. So from this one run to this other run, in which we measure responses, we could go ahead and change multiple factors at the same time. And if we keep doing this repeatedly, meeting certain requirements, then we are going to have a much better design that is going to be a lot more powerful to tell us about main effects, interaction effects, etc. So what is a factorial design? Well, let's talk about full factorial designs. A full factorial design is one in which we have one run, one observation for every combination of the factor levels. So let's say in this example, we have two factors, A and B. They only have two levels, so they can be either 0 or 1. And in this case, we have four possible combinations of these two factors. And therefore, we make four observations, y1, 2, y4. This is what we call a 2 by 2 design, or a 2 to the power of 2 design, which means there's two factors with two levels, each of them. Now, in general, if we denote a design in this way, p to the power of n, what we mean is that there are n factors with p levels. Why do we use this notation? Well, because if we actually compute this number, p to the power of n, that tells you the size of the design, the amount of runs we have, how many combinations of the factors there are. And of course, we could just combine with multiple factors of different levels. So if we have a design like this, 2 to the power of 3 times 3 times 4 to the power of 2, that means there's three factors with two levels, one factor with three levels, and two factors with four levels. And in total, there are 382 observations, 382 combinations of the factors. The main advantage of a full factorial design is that because we have all the possible combinations, it's going to allow us to estimate all main effects and all interactions, all the two-factor interactions, three-factor interactions, 4, 5, etc. It's going to allow us to estimate absolutely everything. The problem, though, is that it can become very expensive. As we have more and more factors and more levels, the whole design is going to grow a lot. And so it becomes very expensive if we test many combinations of the same factors. Now, if this is the case, that we have many factors to study, or our budget is limited and we have to restrict ourselves because we cannot afford the full factorial, then we can talk about a fractional factorial design. And this is one in which we are not interested in all factors, perhaps, or in which we cannot afford, again, the full factorial. And still, we can estimate many of the factors that we are interested in. So the point is that we run only a fraction of the full factorial design. Normally, we split in half. So 1/2, 1/4, 1/8, things like that. And there are standard designs, depending on specific combinations of factors and levels that have desired properties that we will just mention by passing. It's much more efficient because we do not need to study every single combination of the factors. The problem is we cannot estimate all the effects separately. There's going to be a certain degree of confounding. So we're going to start talking about confounding effects, or as in many places they call them, aliasing. So there's going to be aliasing between the effects of multiple factors or interactions. Let's see an example. So here on the left, we have a full factorial design with three factors of two levels, A, B, and C. 2 to the power of 3 is 8 observations. So we have here a full factorial design with 8 observations. In this case, there's no confounding or aliasing. We could collect our data, and we're going to be able to estimate all the main effects, the two-factor interactions and the three-factor interaction indeed. If this is too expensive, or if we are not interested in all those effects, we might go for a fractional design. And the way we denote it is like this. So it becomes 2 to the power of 3 minus 1. In this case, it means that we are splitting the whole design in 1/2. So it would be something equivalent to 2 to the power of 2. That means 4. And so in this case, we have 4 combinations only of the factors. And in this case, we're going to be able to estimate the main effects, but they are confounded with the interactions between them. So for example, in this case, we have that when A equals 0, B is always different from C. And when A equals 1, B is always equal to C. So if we observe a difference between A equals 0 and A equals 1, is it because of A or is it because of B and C? We don't know. Those two effects, the main effect of A and the interaction effect between B and C, is confounded. Now over here in the bottom table, we have a design in which the main effects are confounded with each other. So in this case, we always have, for example, that B is different from C. So if we observe, let's say, a difference between B0 and B1, well, turns out that every time B equals 0, C equals 1. So if we see a difference between B equals 0 and B equals 1, is it because of B or is it because of C? Because it turns out that every time B equals 0, C equals 1, and vice versa. So we don't know what is the effect of B independent of C. We cannot tell the difference. Anytime we see a difference between B equals 0 and B equals 1, there's also a difference between C equals 1 and C equals 0. All the time. So which one is the one responsible for the change in the response? We can't tell because the design does not allow us to study main effects. So this one here is not very good if we're interested in interactions or if we presume that there are interaction effects, but it at least allows us to estimate the main effects. This one over here doesn't even allow us to estimate the main effects. So this one is completely useless. And this whole thing about what effects we're going to be able to estimate from a fractional design and what they are going to be confounded with is what we call the resolution of the design. So depending on which effects we're interested in, we are going to need more or fewer experimental runs and a good design that minimizes confounding between all these factors. And so we have resolutions, for example, resolution 2. In this case, the main effects are confounded with other main effects. This is completely useless. This is the example we had earlier. So if we observe a certain effect of one factor, there's no way for us to be sure that it's because of that factor or because of some other factor. We can't. And it doesn't matter what statistics we apply on it. It doesn't matter how much data we have. It's impossible. We cannot tell the difference between one factor or the other. They are confounded. Then we have a resolution 3 design, which was the one to the right at the top of the screen earlier. And what this is telling us is that the main effects are confounded with two-factor interactions, but they're not confounded with each other. So we could say that there is a main effect of A or there is a main effect of B, and we can tell the difference between one or the other. However, we cannot tell the difference between a main effect of A and an interaction between B and C, for example. Sometimes it's going to be enough because we know or we assume there is no interaction, and then we know that whatever we observe is the main effect. But maybe some other times it's not, and we need to be sure that we can tell the difference between a main effect and an interaction effect. And then we need a resolution 4 design. In this case, the main effects are not confounded with two-factor interactions, but the two-factor interactions are confounded with each other. So if we observe an interaction between A and B, it's confounded, for example, with an interaction between B and C, and we cannot tell the difference between one or the other. However, we know that the main effects are not confounded with any interaction, at least between two factors. If we need even higher resolution, we can go for even more runs, even more combinations of the factors, And so in a resolution 5 design, we have the main effects are not confounded with each other. They're not confounded with two-factor interactions. The two-factor interactions are not confounded with each other, etc., etc. And so the higher our resolution, then the more runs we're going to need. And again, for these cases in which we need a resolution 3, 4, 5, etc., and depending on what factors we have, there are standard designs that follow general principles. Those principles are that we are randomly assigning individuals to treatments. So if we sample one member from the population, we randomly assign them which combination of these factors we are going to try on them. So the point is that the effect of the other factors is expected to affect all treatments equally. If there is a difference between members of the population, let's say by, I don't know, age, then if we cannot control for age, at least by randomly assigning people to one combination or another, what we are doing here is make sure that whatever effect there is of the age is going to be equally distributed across all the other factors, so that we expect them to cancel out, so to speak. If there is a positive effect of the age, for example, and then we distribute people equally by age in here, 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 and here, then that effect of the age is going to just cancel out when we compare the treatments. Replication. In order to minimize random error, we should replicate our study and not just look at one sample, but look at more samples. Blocking is something that may allow us to assign subjects to groups or blocks that could vary, could have a certain variation between them, but we cannot control. So imagine that we have the example of quality of coffee, and we want to try temperature, machine, etc., many other factors. But the point is that for every brand of coffee, we only have capacity for 8 cups of coffee. So every packet is going to allow us to brew coffee 8 times. That's a block. That's a blocking factor, because we cannot try all the possible combinations of the other factors just with 8 possible cups of coffee. So there are certain principles by which we are going to distribute all the combinations of the factors through the blocks, such that we kind of eliminate the possible effect of the package. Because it could be the case that one package is different from the other, and that difference might be interfering with our results. We also have orthogonality. In this case, what it means is that the effect of a factor is balanced across the possible effect of the other factors. And balance of data, the same number of observations per treatment. Now, this is not really a requirement, but it's going to simplify analysis a lot. It reduces our error and avoids incorrect interpretations, misunderstandings, etc. We will talk about this when we talk about regression. And so there are general principles in making a design for a study that in the general case, we don't really need to think about, because there are standard designs already for us. We go to a book or to a certain software package. We say, these are the factors we want to study. These are the effects that interest us. Tell me what is the proper design for my case. And so when choosing a design, we have to think carefully about the possible effects we want to study. Do we care about main effects? Do we care about two-factor interactions? Which two-factor interactions, etc. And then we choose a design accordingly, not the other way around. So it's about finding a compromise between the number of runs that we can afford and the effects of interest. And that's what's going to determine the resolution of the design. And by the way, we are rarely interested in interactions between more than 2 factors, because they're very hard to interpret, and in many cases they're just spurious. Things just happen to be correlated, remember? So once we start looking into that much detail between 3 factors at the same time, 4 factors at the same time, we're just going to see things in there that are completely random. So again, there are standard designs that allow us to reduce the space in the most convenient way and the best way to reduce confounding, etc. And there's plenty of software tools to help us. It's just about telling them what factors we have, what do we want to measure, and just give us the table. And again, just as an example here, let's say we have two-level fractional designs. If we have 3 such factors, then we could run a study with only 4 runs, and that would be a study of resolution 3. So we know we can estimate main effects, but they are confounded with two-factor interactions. Let's say we have 5 factors. Then what this tells us is, if you only care about the main effects and you assume there are no interactions, or you are willing to ignore the extent to which there is an interaction and how it's confounded with the main effect, then you may go with a resolution 3 design, which only requires 8 runs. If you need to go a little bit more than that, and for example, you presume there are interaction effects and you want to estimate them, then you're going to need 16. By the way, a full factorial design here will be 2 to the power of 5, which is 32 runs. And if we have 6 factors, then we can start thinking in the same way and figure out what are the main effects that we want to estimate, 2-factor interactions, 3-factor interactions, do we care about confounding, yes or no, and just choose a fractional design, for example, 32 runs. And again, these are kind of standard designs. So if you have a certain amount of factors of 2 levels, some cases you can find a design for 2 factors of 2 levels, for instance, and 1 factor of 3 levels, or 2 factors of 3 levels. But once you start being a little bit more unconventional, then you start going into the land of optimal designs. And the point is that sometimes these standard designs, these fractional factorial designs, cannot be applied because of the number of factors they include, or the levels of the factors, or because we are interested only in some effects. So for instance, let's say that we do care about the interaction between A and B, and we do care about the interaction between B and C, but we don't really care about the interaction between A and C. So why should we spend runs on trying to estimate this interaction effect? In these cases, there's something called optimal designs. And the point is that they are going to allow us to go for constrained design spaces, in which, for example, we say that if A equal 1, then it cannot be the case that B equal 0, for instance. So think, for example, in the machine for brewing coffee, we cannot have all the combinations of pressure and temperature, for instance, because the machine, for example, doesn't allow us to go into those ranges. Or again, if we are interested in specific effects, but not others, or if we want to reduce even more the number of experimental runs, these designs are optimized for certain statistical criteria that we're not going to get into, but the point is that we can tell them for an arbitrary number of factors of certain characteristics, number of levels, for arbitrary constraints of those factors, for an arbitrary set of effects of interest, we can just run an algorithm that is going to tell us what is the most appropriate design for us. And it's going to be custom made for us. It's going to be tailored to our specific problem. So what should be evident by now is that how good our analysis is and what kind of things we can fairly claim from the data and from the analysis is really restricted by the design, by how that study was designed in the first place. So for instance, we see that there are cases in which we cannot really claim that there is a main effect of a certain factor because it turns out that it's confounded with another factor, or it's confounded with a 2-factor interaction that we did not properly account for, or that we just assumed that didn't exist, and it turns out that it does exist. So again, very important if we are just given a data set and we're asked to see what is in the data set, what possible effects are there, or if they just tell us to answer certain research hypotheses, well, it's very important to understand that just because we have data or a lot of data, it doesn't mean that we can provide answers to all the questions. And just having a lot of data of the wrong kind, it's just going to make us more confident that we have an answer to a question, but actually that answer is incorrect. And what we say is that it's not really a matter of the amount of data, it's really a matter of what data we have, whether it's going to allow us to disentangle the effects of the factors or not, to avoid confounding or not.